Hello, and welcome to Team 7's final presentation video submission for the Deep Neural Networks course at Johns Hopkins University, Engineering for Professional. My name is Carter Edmond, and I will be taking you through the first few slides of our presentation. For our competition, we selected the Whole Tactical Market Prediction competition. You can find more information at the URL listed on the screen. The competition awards a prize of $100,000 for the top submission and ends on June 16th. Further details on the dates will come later in our presentation. There are currently a total of 1,219 teams, and we are recording this for submission on December 7th, 2025. So these are a few of the acronyms that you will see throughout our presentation. The first few being more so related to machine learning in the context of this course, while the latter are more subject matter terms such as efficient marketing hypothesis, the S&P 500, and the relative strength index, RSI. Going into the description and details of our competition. For context, experts have suggested that it is essentially irresponsible to attempt to predict market performance. This is further reflected in the efficient market hypothesis, EMH, which essentially states that everything knowable is already priced, so don't bother trying it. Essentially, they suggest that predicting the market is a pointless task. And this is further supported by the fact that experts have continuously failed to beat the S&P 500 through predictions. Now, the S&P 500 is an indicator for market performance based on the top 500 US companies. However, with recent advancements in machine learning, it is arguably irresponsible to not try to prove the EMH wrong. The nuanced pattern detection capabilities that are shown through the advancements in data science and machine learning suggest it may be possible to create a model that is capable of predicting market performance. The challenge lies in finding and using the hidden trends rather than determining whether these trends exist or not. The whole tactical Kaggle competition encourages users to try to find these patterns through the development of a model that is capable of outperforming the S&P 500. The main constraint is based on volatility and requires competitors to stay within a 120% volatility range of the market. Daily data and a proprietary data set are the core sources for data within the competition used for model training and development. A version of the Sharpe Ratio, which is described later in this presentation, is the core grading metric for the competition. Looking into the hardware constraints for this Kaggle challenge, the challenge essentially restricts users to a Jupyter notebook that runs for no more than 8 hours either on a CPU or GPU. Additionally, internet access is not allowed, although free public data may be used for training and validation of your models. The competition began on September 16th of this year and ends on June 16th of 2026. The final day of submission, however, is December 15th, after which the forecasting period begins, where periodic data reflecting market updates are ran against user submissions. The data contains 8,989 samples and 99 raw features. We will go into further details on these features later in our presentation.
I want to be transparent about the not applicable values on the slide. They do not reflect a lack of work, but rather a significant deployment environment hurdles that we had to overcome before we could even make a valid submission. We faced 3 critical engineering bottlenecks that blocked our earlier submissions. First, the dependency conflict, or the dependency hell. The Kaggle competition environment uses a specific, older version of Scipy that conflicted with modern scikit-learn libraries. every time we tried to run our local model on the server, it crashed with ufunc errors. Since the environment is offline only, we couldn't just pip install fixes. We essentially had to rewrite our entire pipeline to be dependency-free, removing scikit-learn entirely to bypass this. Strict inference API was another one. Unlike standard competitions where you submit a CSV, this required a live inference server. We faced significant challenges debugging the batch prediction logic locally versus on the server often getting submission format errors because the server sent batches of data while our model expected single rows. Lastly, risk metric sensitivity. Our initial models, though working locally, produce returns that, when interpreted as weights by the competition metric, resulted in scores of 0. It took deep analysis to realize we needed to fundamentally shift from a regression approach to a signal clamped approach to register on the leaderboard at all. So while the table shows not applicable, the reality is we spent those weeks debugging a complex production grade deployment pipeline. And this slide reveals the true complexity of the problem. We weren't just predicting price from price. We were interacting with 7 distinct alpha clusters provided by Hull Tactical, specifically node group P and B. Group P contains their proprietary signals. Our model learned to weigh these heavily during high confidence periods. Group V represents variance volatility. Our XGBoost model discovered a critical nonlinear interaction. When Group V signals spike, high volatility, Group T, trend, signals become less reliable. This signal insight allowed us to dynamically deleverage during market stress, which was the key to our high Sharpe ratio.
In this slide, I would like to walk you through our data preprocessing pipeline, which is critical for cleaning the noisy financial data we are working with. First, regarding missing values, we applied a domain-specific strategy rather than a blind fill. We use forward filling for market indicators like price and volatility to maintain the non-valid state, preserving the continuity of the market. For volume data, we filled gaps with zeros, assuming no trading activity. Economic indicators were linearly interpolated to smooth transitions between reporting periods. For feature engineering, we focused on capturing market dynamics at multiple horizons. We generated rolling window statistics, calculating the mean, standard deviation, and min-max across 5, 10, 20, and 60-day windows. We also strictly engineered volatility-adjusted returns to normalize performance against risk, and added momentum indicators, including rate of change and trend slopes over 10 and 20-day periods to capture directional strength. Finally, for normalization, we choose robust scalar over the standard scalar. This was a deliberate choice to handle the significant outliers typical in financial data, ensuring that extreme market events don't skew our model scaling. We also clipped values at the 99th percentile to further stabilize training. This pipeline ensures our deep learning models receive stationary, normalized, and feature-rich inputs without look-ahead bias. Our architecture uses a powerful ensemble approach designed to leverage the strength of disparate modeling techniques. We combine 2 state-of-the-art deep learning models: an LSTM layer with 3 stacked layers, 128, 64, and 32 units, and a custom attention mechanism. This allows the model to selectively focus on relevant historical time steps and capture long-term temporal dependencies. A transformer with 4 encoder layers and 8 attention heads, utilizing positional encoding to identify complex global patterns in the time series data that recurrent models might miss. To complement this, we include traditional machine learning models, XGBoost for capturing nonlinear feature interactions, random forest for robustness, and simple linear regression baseline to stabilize predictions. The final prediction is a weighted average of these 5 models. The weights are determined by their performance on a validation set. Specifically, we use inverse error weighting, so models with lower mean squared errors automatically contribute more to the final decision. This allows the system to favor the most accurate predictor for the current data regime.
Recent modeling problems and challenges encountered and the solutions that we have come up with to address those issues. Throughout this project, we encountered a couple key challenges that required different solutions. So number 1, overfitting was our first major hurdle, particularly on the deep learning models, the LSTM and the transformer that we implemented into our ensemble. The high validation performance wasn't really translating well to the out of sample results. So to address this, we implemented stricter regularization techniques, and also to ensure our models generalized well, we were implementing more comprehensive cross-validation frameworks to really check that the deep learning models were truly performing well and not just overfitting to the data. As well, we found that we had some problems related to regime change sensitivity. So we noticed significant performance degradation during market volatility spikes. Some of the models are better performing in highly volatile times and some perform much more poorly. So our solution to this was to implement regime detection capability with adaptive model switching. So this allows the system to adjust the behavior based on what the current conditions are. So for example, we are using an ensemble method, and the way that the ensemble works is that different models are weighted more heavily, and especially during different regimes, the weights can change. So those better performing volatile market models can be weighted in more heavily during times where the algorithm has detected that we are in a volatile regime. Third, we had some feature instability problems as another challenge. Some of the proprietary features provided by the whole tactical competition showed inconsistent predictive power in different market regimes. We solved this through recursive feature elimination combined with stability analysis. So we ensured we only retrained features with the most robust predictive characteristics and weeded out the less useful features. Also, transaction costs presented a real-world constraint. Our initial high-frequency signals led to excessive turnover in the holdings that the models were suggesting. So, for example, there are some overhead costs to investing and taking out and reinvesting your money. So we implemented a a turnover penalty to discourage the models from taking different positions day to day. So, having a lot of money invested in one day and then quickly flipping to taking it all out, then the next day putting it all back in. There's overhead costs to doing that kind of thing. So we penalize the models for not kind of sticking with what they had done previously. And this results in a more smooth decision-making process during the investment. Also, we implemented position decay. So models can't just sit on a really large investment one way or the other. Over time, those positions start to trend towards or decay towards a more neutral investment strategy. Additionally, we had volatility constraints. So maintaining whole tactical's 120% volatility limit during volatile periods required some extra solutions. We implemented dynamic position sizing along with volatility forecasting to ensure we stay within kind of like an acceptable amount of risk during extreme market conditions. So, reducing the size of your positions that are allowed during highly volatile times. Here's a list of the references where we drew knowledge and inspiration for the techniques used in our project. Finally, for those more interested in the deeper technical aspects of the project, we've included this appendix. It breaks down the research ecosystem from the specific feature categories we engineered, like volatility and momentum, to the rigorous model validation framework we built using 250-day sliding windows. We also monitor strict risk metrics like value at risk and expected shortfall to ensure the strategy remains robust during drawdowns. On the implementation side, our model is built using a scalable Python and XGBoost pipeline designed for memory efficiency. Thank you.